All right, in this chapter, we're going to dive into something called component-based software engineering, or CBSE for short. Now, this is a really big idea that totally changed the game for building large-scale systems. Instead of thinking about software as this one giant, tangled piece of code, CBSE teaches us to see it as an assembly of pre-built reusable blocks, kind of like Legos for software. We're going to explore where this idea came from, what exactly makes a component, and what it's actually like to build with them.
So, here's what we've got on top. First, we'll look at why we even need component-based engineering. Then, we'll get into the anatomy of a component itself. After that, we'll talk about the models and middleware that make it all work, the different processes involved, and finally, we'll wrap up with the challenges of actually putting all the pieces together.
Okay, so to really get why CBSE was such a big deal, we have to start with this question. Object-oriented design was supposed to be the answer to everything, right? It promised us this beautiful world of easy code reuse. But the reality, well, it was a bit of a struggle. Developers quickly found out that trying to reuse individual classes was tricky. A class was often way too specific to its original home, It was tangled up with the rest of the application. And half the time, you had to dig through the source code just to figure out what it did and how to use it. It just wasn't the plug-and-play dream we were sold.
And really, that frustration is the perfect starting point for our story. It's exactly why component-based software engineering came into being. People realized we need to think bigger. It was a very deliberate move to go beyond just single objects and aim for a higher level of abstraction, something that was actually designed for reuse right from the get-go.
Okay, so here's the textbook definition. The process of defining, implementing, and integrating loosely coupled, independent components. Now, those are the magic words right there. Loosely coupled and independent. What does loosely coupled actually mean? Well, it means components aren't all tangled up with each other. They're designed to be these self-contained black boxes. You can use one without having to understand the nitty-gritty details of how it works. You just interact with its public face, its interface, and you don't need to know or frankly even care what's happening on the inside.
So you might be wondering, what's the secret sauce that makes this whole thing work? It really boils down to 4 essential pillars. Think of it like building a house. First, you need the bricks. Those are your independent components, each defined by a clear interface. Second, you need a building code. That's your component model, a set of standards so all the bricks fit together, no matter who made them. Third, you need the plumbing and electricity. That's the middleware, the stuff that connects everything and lets components communicate. And finally, you need the blueprint, the actual construction plan. That's a development process built from the ground up for reuse.
All right, let's zoom in on that fundamental building block. What is a software component, really? What makes it any different from just any old chunk of code you might write?
This table really breaks it down for us. There are 5 key things that make a piece of software a true component. First, it's composable. This just means you only talk to it through its official, public front door, its interface. No sneaking around the back. Second, it's deployable. It's a self-contained init you can actually run. Third, and this is a big one, it's documented. You should be able to know exactly what it does and how to use it without ever looking at the code. Fourth, it's independent. You can drop it into a system without it needing a bunch of other specific components to work. And finally, it's standardized. It has to play by the rules of a component model so it can connect to other components without any surprises.
Okay, I love this diagram. It's probably the most intuitive way to think about how components talk to each other. See that ball? That's the provides interface. It represents all the services and functions this component offers to the outside world. And the socket? That's the requires interface. It represents the services that this component needs from other components in order to do its job. It's such a simple but powerful metaphor, right? For 2 components to work together, the ball has to fit perfectly into the socket. Simple as that. So, let's make this less abstract. Take a look at this data collector component. Its job is to, well, collect data from sensors. Pretty straightforward. Its provides interface, its ball, offers services like start sensor and report. That's what it can do for other parts of the system. But it also has a requires interface, its socket, which shows what it needs. In this case, it needs services from the sensors, things like sensor data and sensor management. This gives you a crystal clear picture of its role, what it does, and what it needs from others to get it done.
Okay, so we've got these neat little components with their balls and sockets. That's great. But how do we actually make sure they can connect and work together in the real world? Especially if they're running on different computers, maybe even in different parts of the world. That's where we get into the rules of the game, the component models, and the middleware that create the entire ecosystem for them to live in. And the first piece of that ecosystem is the component model. Now, this is absolutely crucial to understand. A component model
isn't code itself. It's a rulebook. It's a standard that says, this is how you must define an interface, this is how you name things, this is how you package a component so it can be deployed. Without this rulebook, you just have a chaotic mess of incompatible parts. The USB analogy is perfect here. The USB standard is what guarantees that any USB drive you buy will plug into any USB port. The component model does the exact same thing for software components.
And that leads us to the next piece of the puzzle, which is just a brilliant concept. The implementation of that component model, you can think of it like a mini specialized operating system just for components, right? Just like Windows or Mac OS provides all sorts of services to the applications you run, like file management or connecting to the internet, this component OS, which we call middleware, provides a whole bunch of common services that any component can use.
And these services generally fall into two buckets. First, you've got your platform services. These are the absolute basics, the fundamentals. They handle things like letting components find each other and just talk, the basic communication plumbing. Then, on top of that, you have support services. These are the really handy common utilities that lots of components need, but nobody wants to build from scratch every time. We're talking about things like security, managing transactions, or handling concurrency. The middleware provides all of this as a standard feature, which is a huge time saver. It means developers don't have to keep reinventing the wheel.
Okay, enough theory for a minute. Let's get practical. If you actually decide to build software this way, how does it change your day-to-day development process? Because, as we're about to see, it's a pretty major shift from the old way of doing things.
So in the world of CBSE, you're really juggling two different activities at the same time. Think of it like a kitchen. You have development for reuse, which is like the prep cooks. Their job is to create amazing, high-quality generic ingredients, perfectly chopped onions, a standard sauce, etc., and put them in the pantry. That's your component library. Then you have development with reuse. That's the head chef. They're not chopping onions, they're taking those pre-made ingredients from the pantry and assembling them to create a brand new dish, which is your application.
And that development with reuse process, it totally flips the traditional script on its head. Normally, you'd write a super detailed list of requirements and then start building from scratch. Here, you do it backwards. You start with a rough outline of what you want. Then, the very next step is to go shopping in your component library to see what's already available. And here's the crucial part. You actually change your requirements to fit the components you find. If you find a component that does 80% of what you thought you needed, it's almost always smarter to just tweak your plan to use it rather than trying to build that last 20% from scratch.
Now, this all sounds like a dream, doesn't it? Faster development, lower costs, what's not to love? But there's a catch. A big one. Just grabbing a component off the shelf and plugging it in without truly understanding the world it was built for, well, that can lead to some, let's just say, disastrous results.
And that brings us to the classic and, frankly, terrifying cautionary tale of the Ariane 5 rocket. We're talking 1996. This brand new billion-dollar rocket lifts off, and less than a minute later, it explodes. A total loss. And the cause? A software bug. Specifically, it was a piece of code, a component, that was reused from the older Ariane 4 rocket. On the Ariane 4, which had less powerful engines, a certain data conversion worked just fine. But on the much faster, more powerful Ariane 5, that same conversion caused a number to get too big for its container, a numeric overflow. The component itself wasn't faulty. It did exactly what it was programmed to do. The problem was that the unstated assumptions about its environment were completely broken. It's just a brutal lesson about the hidden dangers lurking in reuse.
So, let's say we've done our homework. We've found the components we need, and we've been careful to validate them. Now comes the final challenge, composition. This is the part where we actually wire these building blocks together to make a real working system.
And there are basically three patterns for putting components together. The first is sequential. This is like an assembly line. The output of component A flows directly into being the input for component B, and so on. Easy enough. The second is hierarchical. This is more like a manager-employee relationship. One component, the manager, directly calls on the services of another component, the employee, to get a job done. And the third is additive. This is where you take two or more components and sort of wrap them up together to create a brand new, bigger component that offers all of their features combined.
But, of course, it's never that easy, is it? This leads to probably the most common headache in component-based development. What happens when the ball just doesn't fit the socket? You find two components that are otherwise perfect for what you need, but their interfaces just don't line up. The data that one spits out isn't in the right format for the other one to take in.
And here's a textbook case of that exact problem.
On the left, we have an address finder component. It's great. You give it a name, it gives you back a full location string. On the right, we have a mapper component. Its job is to put a pin on a map, but to do that, it needs a specific postcode as its input. You see the issue, right? One component is providing a whole sentence, and the other one just wants a zip code. Conceptually, they should work together, but technically, they're speaking different languages.
So how do you solve this? The answer is an adapter. An adapter is basically a little translator component. You can think of it as glue code that you stick between two components that don't quite match. Its only job is to take the output from the first one, transform it into the format the second one is expecting, and then pass it along. So for our address example, the adapter would sit in the middle. It would grab that full location string from the address finder, pull out just the postcode, and then hand that off to the mapper. Problem solved. Communication is now possible.
All right, let's wrap this up and recap the big ideas. So we saw that component-based software engineering was born out of the struggle to make software reuse a reality, moving us beyond single objects to these bigger, standardized, independent blocks. We learned that these components are defined by their provides and requires interfaces, and they live in an ecosystem built on component models and middleware. The development process gets turned on its head. It's all about finding and adapting to what's already there. But as the Ariane 5 disaster showed us, you have to be incredibly careful. And finally, when the pieces don't quite fit, we use adapters as the glue to hold them together. You know, when you really think about it, this whole philosophy, building big systems out of small, independent, communicating parts, it's the foundation for so much of modern software architecture. So here's something to think about. When you look at the world of web APIs and microservices today, how are we still using the exact same core lessons we learned from component-based engineering all those years ago?